And here we're going to take a look at the derivative of logarithmic functions. So if we're taking the derivative of natural log of x, it is equal to 1 over x. So notice that we lose the logarithm in this process. So let's kind of take a look at this and get a review of what our graph of natural log of x looks like. So what we're seeing in terms of rate of change here is we're seeing something very steep and positive right here, and then it kind of levels out. So I'm talking about that slope or that rate of change. So it's increasing across the whole thing. So we're positive here. And then what we're going to see is we're going to kind of approach maybe like a slope of 1-ish right there, and then it starts leveling out and getting closer to a slope of 0. And that whole description there is something steep, like we're very steep out here, probably close to infinity, and then it approaches a slope of 1, and then it starts going towards a slope of 0. That's exactly what we see with our 1 over x function. So what you can see here is here are values of infinity, we're getting closer to 1, and then we start going to 0, and we're seeing that with our outcomes here. Now, something we need to be careful of is that if we're starting with our natural log function, we can't be plugging in negative values. So for evaluating derivatives, we should only be dealing with positive x values. So what you'll see come through here sometimes, or rather, we'll talk about this more, I guess it comes up more in calculus too when we talk about antiderivatives, but you'll see an absolute value symbol come up with these sometimes to show that we need to make sure that x is positive. Going in this direction though, we're okay because we're starting with our natural log function and we're using this to describe the derivative. But just something to keep in mind when working with those two. Now, in terms of a logarithm of any base, then what we'll do is we'll have the 1 over x piece, but also in the denominator we need to multiply by the natural log of the base of the logarithm. So whatever that base a is, that would go in the natural log in the denominator. Which again, we really do have in this case too, is like we're multiplying with the natural log and it's a base e, and the natural log of base e is just a 1, so it just always disappears. But it's technically there. So again, it's really one rule, but it's nice to see that simplified form when we're working with base e. Okay, so let's try out some examples here with taking our first derivative, now using these rules. So, taking our first derivative, this is going to be chain rule because we have at the outside of everything the natural log, and then inside the natural log we have our x cubed plus 3x minus 4. So, taking the derivative of the outside function, natural log tells me to take 1 divided by whatever my input is. In this case, it's x cubed plus 3x minus 4. And then we're going to multiply by the derivative of the inside function, which would be a 3x squared plus 3. And what we could do is just combine that into a numerator of 3x squared plus 3 over x cubed plus 3x minus 4. And that'll do it. All right, a little more complicated here. We're going to take the natural log, so that's what we have at the outside of everything. And then inside, we're going to need some quotient rule, a little product rule as well. So I'm going to write this out in long form. So chain rule, derivative of the outside function, so derivative of that natural log tells me to take 1 divided by whatever's inside the parentheses. And then we're going to multiply that by the derivative of that inside function, x squared times sine x over 2x plus 1. Okay, we have a complex value on this left-hand side, which we can adjust by multiplying the numerator and denominator by that 2x plus 1. So rearranging that, we'll have 2x plus 1 up in the numerator divided by x squared times sine x. And then we're going to use the quotient rule. So low d high, so 2x plus 1 times the derivative of that numerator, which we're going to have product rule here. So derivative of one times the other, plus keep one and derivative of the other. So I have 2x from the derivative of x squared, then I keep sine x the same, plus keeping x squared the same, derivative of sine x is cosine x. Okay, so that's my low d high, and then I'm going to go minus high d low. So x squared sine x times the derivative of 2x, which is just a 2. All over low low, which is a 2x plus 1, quantity squared. And something that's nice is that if I look at this left-hand factor, that 2x plus 1 over x squared times sine x, I have a common factor of 2x plus 1 that can cancel out with the 2x plus 1 in the denominator. So I'm going to cancel out, and that's going to leave me with just 1 in the denominator instead of a 2x plus 1 squared. Okay, then from there, what I'm going to do is I usually start by seeing if there are common factors I can take out of the two terms, but I'm not seeing anything there. So I'm going to go ahead and do is multiply out. I'm going to go ahead and FOIL this 2x plus 1 with the 2x sine x, x squared cosine x. So in the numerator, 2x times 2x sine x is a 4x squared sine x. 2x times x squared cosine x, so 2x cubed cosine x. 1 times the 2x sine x and the x squared cosine x. All subtracting with x squared sine x times 2. So I have minus 2 of those. Minus 2x squared sine x. All over, and we have this x squared sine x times 1, 2x plus 1. Okay, then I'm going to see if there are any like terms I can combine, and it looks like we have this x squared sine x as common terms that we can combine together. But everything else is going to need to stay separate. So for our derivative, let's see, I'm going to order these by the degree on x. So I'm going to put that 2x cubed cosine x first. Then we have a plus x squared cosine x. Combining my like terms, I'll have a plus 2x squared sine x. And then I'll have a plus 2x sine x. All over x squared sine x times 2x plus 1. Just to investigate a little bit, I'm going to do some factoring by grouping here. So as a refresher, that's where if we have 4 terms, we kind of split it up. And what I'm seeing is on the left-hand side, I have common factors of x squared cosine x. And that's going to leave me with a 2x plus 1. And then on the right-hand side, I have a plus 2x sine x as common terms, which would leave me with an x plus 1. Okay, nope, we're going to leave it like that. If this happened to both have a 2x plus 1, that would be real nice for kind of factoring by grouping, and maybe we'd have some cancellations, but we're not having that here, and that's totally fine. So just something to think about of simplifying further, but sometimes we'll just be stuck, and in this case we are, so we'll just leave it like that. Okay, last one here, finding the slope of the tangent line. So this is where we're evaluating just the slope. So we're taking the derivative at the value x equals 1. And I've used the notation f prime of 1 for this, which is absolutely correct. I do want to show you another notation that could be used, which is the idea of looking at dy dx. So our other notation of what a derivative is, and what you might see is this with a tall line that goes x equals 1. So what this is reading as is that first derivative of y with respect to x at x equals 1. So what we could do with this is then evaluate the derivative. So log base 2 is our outside function. Inside function, we have a 3x plus 1. So derivative of the outside tells me to take 1 over my input, which we're keeping as 3x plus 1, times the derivative, or not the derivative, the natural log of the base of 2, times the derivative of 3x plus 1, which is 3. And then what we're going to do is evaluate this at x equals 1. So we're going to plug in x equals 1 in this next step. So I have a 3 in the numerator over 3 times 1 plus 1, so that's a 4, natural log of 2. So that would be our slope for our function at x equals 1, and if you wanted to, you could take this to a decimal just to get an estimate of what that slope is looking like. So it's just a little over a positive 1. And that's how we'll use those derivatives of logarithmic functions.